Today I'm going to talk about Puppet server specifically, and containers. And before that, I'm going to talk about myself. So, who am I? My name is David Moreno Garcia. I'm a happy CERN employee working in the computer monitoring group. And for the last year, I've been working in implementing a multi-tenancy solution for us. And I suppose that this is something that some of you are not familiar with. So in this presentation, I will go in details why these two words are important and how we have been working in improving the security of the infrastructure. I won't mention what a CERN is. I assume that everyone knows because we are actually in the main auditorium. So I'm going to talk about config management. CERN is a big organization. We have, our section manages the configuration for 40,000 nodes, approximately. And for doing that, we have an infrastructure with around 200 dedicated servers. In those servers, we run Puppet. Puppet is an open source solution that allows us to use a declarative language to specify the configuration of all our machines. And we are using the community version since 2013. Other tools that we use is Foreman, PuppetDB, we use Rundeck, among others. And to specify the configuration on all the nodes, we rely on the work on 500 service managers, more or less, all of them with developer access. And this is actually a problem. Ideally, Puppet is thought to have small teams of power users that are the ones that are going to manage the configuration. And the most important thing is that they are going to trust each other. It's not like we don't trust our service managers, but it's a big group. So how growing out of control can be a problem? This is a representation of our community. It's an heterogeneous one, different skills, different knowledge base, some of them working even in different countries. But all of them work in what we can call teams. Here we have OpenStack, Ceph, we have EOS, we have Hadoop also. So all the teams have dedicated resources. They have their own servers, and they have their own repository. It's a GitLab repository where they are going to store the code or the configuration for the nodes. Let's imagine for a moment. Now we have a malicious user that arrives to his computer, steal the credentials of one of our service managers here at CERN. And now this attacker could, for example, change the configuration in the repository of EOS. Obviously, now that the configuration has changed, once an EOS server tries to get the configuration, we can say that it's compromised. Now he can do whatever he wants. But what actually happens here, given the infrastructure that we have, is that all of the servers of the infrastructure, the 40,000 nodes, are going to be compromised. So how this kind of attack works? We mentioned that these teams are working in groups, in teams with dedicated resources, but all of them share one thing, and that is our Puppet masters. The Puppet master is the server that is going to actually compile all the code, generate a configuration, and deploy it to the nodes. So when a node requires that configuration, what is going to happen is that it's going to start sending several requests. The first of them is going to be node, that is going to retrieve information about the node. It's also going to send a request to the endpoint file metadata, still inoffensive. But when it sends the catalog request, this is a moment that is quite tricky, because this is first a long query, and secondly is a query that is going to has the possibility of execute code in the Puppet master. If we reach to this point, and the configuration in GitLab is compromised by this attacker, what could happen is that someone could kill the Puppet server daemon, the actual entity that is going to compile the code, replace it with a honeypot, and from that moment we can say that the server is compromised. Now, if another node is requesting the configuration, the attacker could eventually send anything that he wants to the node. So that configuration is going to be, again, compromised, And the attacker could say, for example, change this configuration, execute this program, do whatever I want to do. So again, the node is compromised. This is a big problem. So we found out 2 different solutions to mitigate this problem. First of all, we can increase the security of the masters. Easy to say, it's a bit more difficult to achieve. And we could also do this. We can split our Puppet masters and having dedicated masters for the different teams. Cool. We prepared 2 prototypes. The first of them is using containers, and it's going to tackle the first problem. We want to increase the security, and we also want to change the minimum parts in the infrastructure. This is the infrastructure nowadays. This is a very simplified view in which we have the agents in the nodes that are going to connect to the masters. And the master is going to use 2 different services. One is Foreman, that stores information about the nodes. And the second one is PuppetDB, that stores Puppet-produced data. Both of these services define access control lists, so only the masters can connect to them. And also, all the configuration for all of these elements is produced by Puppet. So we wanted to keep this because we are happy with it and we have been using it for years. So we thought about doing something like this. We know that only one request is responsible for these kinds of attack. So we can send all the safe traffic to the former Puppet masters and create a new one, a catalog master that is going to attend only to catalog requests. So how this master works? First of all, we are still using Puppet. So what we are going to get for free is all the configuration that we have and also all the integration with the central monitoring. The difference, now the Puppet server daemon is not running in the host, it's running in a pool of containers. And we have two different kinds of containers here. Active, those ones, or inactive ones that are just going to be there to be ready to replace the other ones. We have also an HE proxy container that is going to balance all the traffic inside the master, and it's going to do different things also. Imagine that now that we have a request, like in the previous slide. That request goes to a container, and we don't know if it's a good one or it's a malicious one. We don't have a way to know that. But let's imagine for a moment that it's malicious. HE proxy is going to do one thing, and it's that the moment that the request finished, the moment that we have compiled a catalog, the container has to disappear. So that way we know that if the attacker changes anything in the container, now we are safe. That changes disappear. Another thing that it's going to do is get one of the inactive containers and make it active, so we can attend new requests. And finally, it's going to spawn a new one. So again, we are in the same position that we were before starting the execution. We deployed this, and we wanted to see something like this. Here we are showing the amount of time that we need to compile a catalog for a given node. And ideally, at some point, we are going to see like all the times get stable, more or less 40 seconds, like in production. It would be nice. Actually, we saw this. The times were quite high and quite stable, and we had no idea about why. So we had to analyze the problem and find out where the time was going. And this is a summary of it. So the catalog compilation time, the amount of time compiling the configuration for a node, was more or less the same like we saw in production. We have a 5% caused by the kinds of deployment that we had before. We have a Puppet master with a single process, the Puppet server. Now we have a Puppet master with the same characteristics, but running a pool of containers, so it's going to be a bit more slow. But most of the time was going to the warming up of the Puppet server. Puppet server is Ruby code running in a Java machine, and one of the things that happen when you get a request, the first request, is that it's going to load into memory all the resources that it needs to execute a catalog, that it needs to compile all the configuration for a node. And as we were constantly killing the containers, we were constantly loading those resources. We tried to mitigate the problem and get some seconds out of it just by changing configuration or also by using container snapshots. At the end, we decided to move to a different prototype. And in this case, we are using Kubernetes. Some of you can say, for example, hey, David, this is a more standard approach. It's modern, we like it, has advantages, we agree, but it also has a lot of drawbacks. So we have a list here. In this approach, we are not killing containers anymore. So obviously, we are not going to have this warm-up time, because all the containers are going to live as much as we can. We are going to split the infrastructure. So that means that first, we still need this pool management, but we need also auto-scaling. As the infrastructure is split between different teams, we don't want a human to control what team has too many resources or what team needs more. We want to do this automatically. And one thing that we get that is quite interesting is that it's going to allow us to deploy new versions of Puppet just for single teams. So we can test and then deploy for everyone. Drawbacks is a long list. We are not backed by Puppet anymore, so all those access control lists, all the configuration that we got for free, we have to do it again. We have to deploy it somehow. We need changes to the Puppet agent code. This is just for sending more information from the node to the masters. We require changes in ingress controller. We are testing actually both Nginx and traffic. And in both cases, we need to process all the information that is coming from the agent and use it for balanced traffic. And this is something that is not there by default. We need to integrate everything again with the central monitoring. There is some kinds of integration already in our deployment of Kubernetes, but we have to add more. We have to add the processing that we have with Puppet. We need also a release management tool. And finally, there is a huge learning curve. In our section, we are experts in Puppet, but not that much in Kubernetes. So we have to talk with different sections already using it, with cloud, like Danny's team, to make this kind of deployment. But we went ahead and we prepared this. It's what I like to call Puppet nitties. And what is in here is a single cluster in which we have different splits, namespaces in Kubernetes for different teams. In this case, we saw Ceph and EOS. In these namespaces, we are using the same containers that we used in the first prototype with a single difference. In this case, all these containers are going to actually validate that a request that is arriving from a node can be executed in that container. And secondly, we have the ingress controller that is going to do header management. So the information that is going to come in the headers of the request from the node is going to be used to balance the traffic. And also we are going to set specific headers, custom ones, to make a Puppet work without having to deal with SSL validation in that part. To manage this deployment, we use this Helm, this release management tool. And the reason for this is that it's a simple one, and most important, it's been used by different sections in the IT department. It's quite easy to adjust the configuration, as it's using templates, and allow us to dynamically, in each of the releases that we are going to make, just make small changes in the configuration of the servers. And finally, we have a CERN-made plugin for Helm that is based on Barbican. That is quite nice, actually. And that is going to allow us to handle the secrets in the cluster and store them in the GitLab repository that is used for storing the charts for Helm on all the configuration that we have. So, just arriving to the end of the talk, summing up, we are actually working in this prototype and we are reaching the test phase. We know that the times are going to be better, but we still have to send real traffic. And for doing that, we are missing some bits that hopefully are going to arrive in the next weeks. We have an initial monitoring integration. So all the logs for the servers are currently being sent to the central monitoring after being processed by Fluentd. That is the tool that we use. We don't have auto-scaling yet. It is a feature that the cluster that we use supports, but at this moment, we don't need it. So it's something that will arrive in a later phase. And finally, we are still open to alternatives. As I mentioned, we identified two solutions. but we know that probably there are more. So if you think that we can do better, I'm pretty sure that we can. And if you have any idea, we are welcome to them. So thank you again for having me here and for your attention.